Alrighty, folks. So today we're going to be starting up on Chapter 4 with Section 4.1, which is all about linear approximations. Right? And it's actually using a formula that we've pretty much already talked about. Right? We've gone from the idea that the limit as delta x goes to 0, so the derivative of f, limit of delta x goes to 0 of this guy. All right, we've called it x before, but for this particular application, it makes some sense to call it delta x. And we've talked about how before that means that if delta x is small, f prime of x is really close to this difference quotient. Right? And the smaller delta x gets, the closer that equality is. Right? And so that is everything that's behind the formulas for linear approximation that we have. The first one the book gives is that f of a plus delta x minus f of a, which is what they call delta f, is approximately equal to the derivative of f at a times delta x. And equivalently, sometimes what you want to do is know about just that changed number, not the difference, but the change. And that's going to look like, really it just requires, it's not going to be equal, it's going to be approximately. Even with the squiggly equal sign, we can still add numbers to both sides. So we get this formula, right? So these are both linear approximations of using the derivative. And so this is linear approximations. And then this section also introduces this thing called a linearization. There we go. It's a tough word. And that says for x close to a, f of x is very close to L of x, which is equal to f of a plus f prime of a times x minus a, and this should be an x, not an a. And keen-eyed folks might notice that this is in fact the tangent line, the equation for the tangent line. So it turns out that if you're really, really close to a, the tangent line for a might be a simpler way to think about the function as long as you're staying really close to it. Later on, our last section that we'll talk about, just to give a far into the future, or at least a few weeks into the future, look at where we're going, we're going to talk about something called the Taylor series, or Taylor polynomials, rather. We won't be getting into the series part of it. But Taylor polynomials, which are, what if we still want to be really close, but we don't want to be a linear polynomial, maybe we want to be a quadratic polynomial, or maybe we want to be a cubic polynomial. So that's something we'll be getting to later. For now, we're just sticking with these linear approximations. right? So one type of problem that we might get is to estimate the difference between the square root of 99.9 and 10. Right? So, one thing to notice is that these don't really look too much alike, but if we're going to use this in the section on linear approximation and we're talking about a difference, we better be talking about a difference that looks like this, right? So we need to think about a function that would give us both of these values when we plug different things into it. And so one of the things that might occur to us is that if f of x is the square root of x, then the square root of 99.9 is equal to f of 99.9, and 10 is equal to the square root of 100, so that's f of 100. Right, so both of the numbers that we're looking at estimating the difference of can come from the function, right? So now it behooves us to figure out which of these is a and which of these is a plus delta x and a. Right, so this is where getting practice with these types of functions come in handy. Because as you do, you'll realize that you always want to pick the simpler number to be a, right? That's the whole point of this linear approximation. If we were okay with figuring out what the square root of 99.9 is, then we wouldn't have to approximate it. We could just do it flat out, right? But the square root of 100 is a lot easier. So we're going to say that a is 100, which means that the other thing that we're plugging into f has to be a plus delta x, right? So we figured out f of x, we figured out a, right? So now we need to find the derivative and delta x. Delta x is going to be the easier one. If we take a and we subtract, well, rather, let me do it the other way around. If we take a plus delta x and we subtract a, right, so this is a plus delta x minus a, this is negative 0.1, and this is clearly delta x, so since these two guys were equal, delta x has to be negative 0.1. Right? So now we have delta x, we have a, we need to find f prime of a. So that means finding f prime of x, right? So one of the things, reminder, this is x to the 1/2. So it's just a power function. We can use the power rule. All right, we bring the power forward, and then we go down by 1 to get 1/2 times x to the negative 1/2. So we really want to know f of a. A is 100, so that's going to be 1/2 times 100 to the negative 1/2. Right, remember the negatives just bring it to the bottom of a fraction, so that's going to be 1 over 2 times 100 to a half. The half power means the square root, so we get 10 there. So f of a is 120. right? So now we go back up here to our linear approximation. So we want to know the difference between the square root of 99.9 and 10. We figured out that that was f of 99.9 minus f of 100. And according to this approximation, that's going to be approximately equal to, let me get all the steps in here, that's delta f, which is going to be approximately equal to f of a. So a we said was 100 times delta x, which we said was negative 0.1. So that's going to be 1/20th times negative 1/10. So we get negative 1/200. Right? So using this formula generally boils down to taking our question and making it fit this. That should usually get us f, a, and delta x. Then we've got to use calculus to get the derivative of f. And then we plug things into this side of the equation. And we know that they are approximately the same. And when we're trying to estimate, approximately the same is good enough for us. So let's get another problem in here. So we're going to have a revenue function, which is a function of the price of the tickets. So we're going to find the revenue when tickets cost $5 a piece. And then we're going to approximate the revenue if we were to increase that price by 50 cents. Right? So as we read over a word problem, find usually means we want the exact value, right? It's different from estimate that we had up here. Estimate means that we can do an approximation, we can get close. Find means we want it exactly, right? So this part of the problem is just asking about R of 5. Right, because P is the price of tickets. I probably should have said in dollars here. That would have been good. So we want to find the revenue when tickets cost $5. R of P is the revenue given as a function of the price of a ticket. So we just need to plug 5 into that function. Right, this is going to be 10,000 minus 4 times 125, which is 10,000 minus 500. So we get $9,500. Right? So that's our revenue at exactly $5, right? And then the next question, question B here, first off says approximate, which is the clue that we should be using, one of the formulas from this section. And it wants us to approximate specifically the revenue, right? If we take the price we had before and add 50 cents to it, right? And if the price is in dollars, 50 cents translates to 1/2, right? So this is 50 cents, given that 1 is $1, right? So we want to approximate something that looks like this. So we go back up to our formulas. That looks a lot like this guy here, right? Looks a lot like this one in particular. So if we go back here, this tells us that the f of x, or the function that we care about, we don't necessarily need to use f, is our function, right? So we have that from up here. We also should be able to find a and delta x, right? And again, as before, a should be something that it's easy to plug into, or perhaps that we've already figured out, right? So we already know what happens when we just plug 5 in. We figured that out in this first part. So again, we look back up at our formula here. We want our function of a nice value plus something else, and that something else is our delta x. So that means that our delta x should be 0.5, right? Now, or really delta p. All right, so p plus delta p. If we translate our formula into this, we get that that should be r. There we go. Got myself confused. Too many p's. All right, it's just that p takes the place of x here. It doesn't take the place of all the variables. All right. So our formula from above says that f of a plus delta p, which, since we're dealing with a function named r and a variable named p, means we're looking at r of a plus delta p, is going to be, it said f of a above, but this time our function's name is r. So it's r of a plus, it said f prime of a above, but again, our function's name is r. So we get the derivative of r at a, and then, I went too far back. It said delta x above, and now we have a variable of p, so we're going to put delta p there, right? So that's just a translation of this statement right here, where all of our f's were replaced with r, because that's the name of the function in our problem, and all of our x's were replaced with p's, because that's the variable in our problem, right? If it makes you feel better when you're doing it, you can instead take the problem and translate it into f's and x's. It's hard to pluralize those letters. But either one of those directions is perfectly fine. It's just a matter of what you're comfortable with. They're all just names. Right? So, since this is what we want to find, or at least what we want to estimate, right, that means we need to figure out what this is, which means we need the derivative. All right, so let's go back up here so we can see what r of p is. So, the derivative of p, that's just a polynomial. The first term is linear, so we can just take the coefficient. The second term is a power, so we need to bring that 3 down and then make it go down by 1. So then r prime of a for us is 5. So we plug 5 in. Twelve times 25 is 300. So we get 1,700. So then we figure out that the thing that we want to estimate is approximately r of a, which we figured out above was 9,500, plus r prime of a, which we figured out right here was 1,700, times delta p, which the definition of the problem tells us is 0.5. So that's going to be 9,500 plus 850, which is going to be 10,350. So that's going to be our approximate revenue if we increase prices by 50 cents, right? So those are the two main sorts of things that we do with linear. Either it's set up so that we're trying to estimate or approximate the difference between two things, or it's set up that we're trying to estimate or approximate the effect of changing the input of a function by just a little bit. And then we use the two different versions, either this one or this one, of the formula for linear approximation. So next up, we'll be talking about extrema, maxes and mins and all those sorts of things, that you've probably seen some in pre-calculus, but now we're going to be able to do it for a bunch of different types of polynomials. Before, you probably just did it for quadratics, and now we're going to be able to do it about any function we can take the derivative of. But that'll be for next time, and I'll see y'all then.